Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the nascent world of electronic computation following the Second World War, a period of fervent innovation and architectural experimentation, the logical blueprint for the modern computer had begun to solidify. The stored program concept, articulated in documents like the first draft of a report on the EDSAC, provided the foundational paradigm: a machine that stored both its instructions and its data in a unified memory, allowing for the manipulation of its own programming. Yet, this elegant theoretical framework concealed a formidable practical challenge, one that resided in the very heart of the machine, the control unit, its component tasked with interpreting instructions and orchestrating the flow of data through the arithmetic and logical units, was in the early 1950s a bastion of ad hoc engineering. Its implementation typically consisted of a bewildering and intricate web of hardwired logic gates, a bespoke creation for each machine that was monumentally difficult to design, debug, and impossible to modify without a physical reconstruction. It was within this context of artisanal complexity that Maurice Wilkes, a central figure in British computing and the leader of the team that built the successful EDSAC computer at the University of Cambridge, presented a paper of profound and enduring significance. His 1952 address at the Manchester University Computer Inaugural Conference, titled with a confidence bordering on prophetic, "The Best Way to Design an Automatic Calculating Machine," offered a solution of stunning elegance. Wilkes proposed a method, which he termed microprogramming, that would transform the design of the control unit from a craft of intricate wiring into a systematic, disciplined process. This was a conceptual leap that introduced a new layer of abstraction between the machine's instruction set and its physical hardware, a principle that would dominate computer architecture for over 3 decades and whose intellectual echoes persist in the most advanced processors of the current era. The genesis of Wilkes' insight lay in his direct, hands-on experience with the limitations of contemporary design. The construction of the EDSAC, which entered regular service in 1949 as the first practical stored program computer, had provided him and his team with an unsparing education in the difficulties of realizing the stored program concept in tangible hardware. While the EDSAC report supplied the abstract, logical organization, it offered scant guidance on the practicalities of implementing the control circuits responsible for executing the machine's instruction set. For each instruction, such as adding a number from memory to the accumulator or storing a result, a specific sequence of elementary hardware operations had to be triggered in a precise temporal order. These elementary steps, or micro-operations, involved opening and closing electronic gates to route data between registers, the memory, and the arithmetic unit. In EDSAC, as in its American contemporaries, this sequencing was managed by a complex, monolithic, and inflexible collection of interconnected vacuum tubes and logic circuits. Modifying or correcting the behavior of an instruction was a daunting task, requiring a soldering iron and an intimate, almost intuitive, knowledge of the machine's physical wiring. The process was error-prone, time-consuming, and scaled poorly with increasing instruction set complexity. Wilkes recognized this hardwired control as the primary bottleneck, a source of profound engineering travail that limited the ambition and reliability of future machines. He sought a method that would impose order upon this chaos, a systematic approach that would render the control unit as logical and modifiable as the programs it was designed to execute. The solution presented in his 1952 paper was as simple in its conception as it was revolutionary in its implications. Wilkes observed that the execution of any single machine instruction could be decomposed into a sequence of more fundamental, primitive hardware actions. He proposed to codify these sequences, the microprograms, and store them in a dedicated, fast, and unalterable memory, which he termed the control store. In his initial formulation, this would be a diode matrix, a form of read-only memory or RM. The operation was elegantly straightforward. When a machine instruction was fetched from main memory and placed in the instruction register, the operation code of that instruction would serve as an address into this control store. This address would point to the starting location of a specific microprogram, corresponding to the fetched instruction. Each entry in the control store, a micro-instruction, would contain 2 pieces of information, a set of bits to directly control the various gates and micro-operations of the hardware for 1 clock cycle, and the address of the next micro-instruction in the sequence. Thus, executing a machine instruction became a process of fetching a sequence of micro-instructions from the control store, each one orchestrating a single step of the data path until the entire operation was Wilkes detailed a concrete design involving a pair of decoding matrices. The first matrix, would take the machine's operation code and select the correct starting micro-instruction. The second matrix would decode the output of the control store to generate the individual signals to activate the computer's functional units. This architecture effectively created a computer within a computer. An outer machine, visible to the programmer, possessed a potentially rich and complex instruction set architecture. This outer machine was, in reality, being interpreted by a simpler, faster inner machine whose own native instructions were the micro-instructions stored in the ROM. This was the critical abstraction, the instruction set architecture. The very identity of the computer from a programmer's perspective was decoupled from the underlying physical microarchitecture. Designing a computer's control logic was no longer an exercise in complex combinatorial and sequential logic design. It became a programming task. The intricate ballet of electronic pulses was now choreographed by an orderly, stored sequence, a microprogram that could be designed, tested, and corrected in a systematic fashion before being permanently encoded in the diode matrix. The immediate impact of Wilkes' idea was felt most directly within his own laboratory. While a 1952 paper presented the concept, its first full implementation was in the design of his next machine, the EDSAC-2, which became operational in 1958. The contrast with the construction of its predecessor was stark. The control logic of EDSAC-2 was designed systematically using microprogramming, making the entire process vastly more manageable and less prone to error. Debugging a faulty instruction became a matter of identifying and correcting a flawed microcode sequence, a task of logic and programming, a world away from the physical rewiring required for EDSAC-1. This successful implementation served as a powerful proof of concept, and the idea began to disseminate through the small, interconnected community of computer architects. The paper itself, presented at a major conference, ensured that the concept reached the key figures who were grappling with the same design challenges across the Atlantic and in continental Europe. The true golden age of microprogramming, however, arrived in the following decade with the advent of the commercial mainframe. The most consequential adoption of the technique was by IBM in the development of its revolutionary System 360 family of computers, launched in 1964. The strategic goal of System 360 was unprecedented: to create a range of machines, from small, inexpensive commercial models to powerful scientific behemoths, that were all software compatible. They needed to share a single, unified instruction set architecture, allowing programs written for one machine to run on any other in the family. This ambition presented a massive engineering dilemma. A single hardwired control unit design would be far too expensive for the low-end models and insufficiently powerful for the high-end. Microprogramming, championed by IBM architect Gene Amdahl, provided the perfect solution. Each model in the System 360 line implemented the same complex instruction set, but they did so with vastly different underlying hardware and microprograms. The low-end Model 30, for instance, had a very simple, serial, and inexpensive microarchitecture, and it relied on a large and intricate microprogram stored in a capacitor read-only store to emulate the full System 360 instruction set. In contrast, the high-end Model 75 possessed a much faster, more parallel hardware implementation with many functions wired directly, requiring a smaller and simpler microprogram. This ability to trade hardware complexity for microcode complexity enabled IBM to deliver on its promise of a compatible family of machines spanning a wide range of cost and performance points. This success cemented microprogramming as the dominant design paradigm for the era of complex instruction set computers, or CISC. Architectures like Digital Equipment Corporation's VAX famously expanded on this, boasting incredibly complex instructions, such as one to evaluate a polynomial, whose implementation was feasible only through elaborate microcoded sequences. The further development of writable control stores even allowed for dynamic microprogramming, enabling machines to be reconfigured to emulate different computer architectures entirely, a powerful tool for research and diagnostics. Every dominant paradigm eventually invites a critique, and the trade-off at the heart of microprogramming was its performance. The interpretation layer, the process of fetching and decoding microinstructions, introduced a significant overhead. The execution of a machine instruction via microcode was inherently slower than its execution via dedicated, hardwired logic. This performance cost became the central focus of a new school of thought that emerged in the late 1970s and early 1980s. Researchers like David Patterson at the University of California, Berkeley, and John Hennessy at Stanford University began to advocate for a different approach. Their work on reduced instruction set computers, or RISC, was built on a counter-argument. They proposed that a smaller, simpler set of instructions, each one simple enough to be implemented directly in fast, hardwired logic and typically executing in a single clock cycle, would lead to faster overall performance. More complex operations could be synthesized by an optimizing compiler, shifting the burden of complexity from the hardware back into the software. The confluence of increasingly sophisticated compiler technology and the falling cost of fast semiconductor memory made the RISC philosophy economically and technologically viable. For general-purpose processors, the tide began to turn. The elegant complexity of CISC instruction sets, made possible by microprogramming, started to appear as a performance liability compared to the lean, swift execution of RISC designs. By the 1990s, the era of classical microprogramming, as the primary method for CPU control unit design, was drawing to a close. Yet, to declare microprogramming obsolete is to miss the enduring power of its core principle. The ghost of Wilkes machine still animates the most sophisticated processors of the modern day. The dominant x86 architecture used in personal computers and servers, for example, presents a classic CISC interface to the programmer, with a legacy of complex instructions accumulated over decades. Internally, however, a modern Intel or AMD processor is a radically different beast. These processors are fundamentally RISC-like execution cores. When a complex x86 instruction is fetched, it is first translated by a decoder unit into a sequence of simpler, internal micro-operations, sometimes called UOPs or OPs. It is these RISC-like micro-operations that are then fed into a highly complex, out-of-order, superscalar execution engine. In effect, the processor is still emulating the complex x86 instruction set using an internal, simpler instruction set. This is the direct intellectual descendant of Wilkes' 1952 insight. The abstraction layer he first proposed remains, albeit transformed into a dynamic translation process to bridge the gap between a legacy instruction set and a high-performance modern core. Furthermore, in specialized domains, microprogramming in its more classical form persists. Graphics processing units, with their massively parallel architectures, rely on microcode-like mechanisms to manage their thousands of cores. Many embedded microcontrollers and digital signal processors, where design cost and flexibility are paramount, continue to use microcoded control units. Maurice Wilkes' 1952 paper stands as a landmark in the history of computing, a work of profound clarity and foresight born from the messy, practical realities of building the first generation of digital machines. He looked upon the ad hoc, tangled complexity of the hardwired control unit and saw a path to order and systematic design. The solution he proposed, microprogramming, was more than an engineering trick. It was the introduction of a new level of semantic hierarchy in computer architecture. It established that the machine's perceived identity could be an abstraction, a programmable layer distinct from its physical substrate. This principle of interpretation and abstraction not only defined the trajectory of mainframe and minicomputer design for a generation, but also continues to resonate in the architectural compromises and solutions that enable a remarkable power of contemporary computing. The best way to design an automatic calculating machine was a bold title, yet history has shown it to be an understatement. Wilkes had articulated one of the most powerful and lasting ideas in the art of machine design, proving that the most elegant way to build a complex machine is sometimes to first imagine a simpler one hidden within.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.